Basically, we'll be covering the Modular Construction Handbook, which is a collaboration between Monash University and the MEIG. So our co-authors of this are James Murray Parkes and Dr. Yu Bai from the Monash University. It's a big collaborative effort between the two organisations, and of course there's a lot of help from our sponsors as well. So we really do need to thank all these organisations without which the handbook would not have been possible at all, and they provided so much support through the entire process and all the hard work that went into it. So a bit of an overview of the handbook. What we find in modular construction in the current state of the construction industry is that there's not a guideline or a set of guides to actually design to. It makes it difficult as a designer to know what standards you should be designing to, and at the same time as a client or an investor, how do we specify what our building is going to be? How do we know that we're getting something that's of quality when it is a modular construction? So this is the main problem which we're trying to get around with the new guideline, along with just trying to improve modular design and hopefully help that to be rolled out on a more wider scale. So a few of the special aspects of modular construction which we need to consider and which of course are covered in the handbook are included here. I'll go into those in a bit more detail. But if you do look in your packs that you received today, you do have USBs which have the whole handbook on there. So you're able to go through, start reading through them, and hopefully taking some of the ideas and some of the concepts into your designs when designing for modular. So the approach we took with actually writing the handbook is very much going back to the, I guess you could say, the physics, the engineering, the basics of it, and looking at how we're designing the structure, maybe in a bit more detail than what you might expect from some of the standards that are out there today. So for instance, when we look at material degradation, we're looking at fatigue, corrosion. We've gone to the most recent research that's been conducted by other institutions around the world to see what's best practice and adding that on to what's currently specified by, say, Australian standards or other standards that we reference. And then this also gives us the opportunity to update the standard as new research is developed and basically keep making sure that it does stay relevant. Obviously very important with modular construction is the transport. So we're taking basically complete modules, the concept of modular design, and transporting these to site. So the loads that they experience in that process need to be considered, any damage during transport, how we're transporting them. These are all important considerations that we outline in the handbook as well. And for us, modularisation really means taking it a step further and looking at the whole life cycle of the building. So when we finish up with our design, we don't usually look at the next stage. Are we going to be able to recycle, reuse, move those modules? That is an opportunity with modular design, so we cover that and try and make that another opportunity to add to the modular designs that we're recommending. And it's really the sustainability of modular that gets us interested in that we're reducing the amount of resources on site, we're building in a more efficient, less resource-intensive way, and eventually you are actually able to see the benefits of that in terms of construction time and in terms of the construction costs, if we can get past some of the maybe negative connotations that are associated with modular at the moment. So this is some testing of or modelling of a module based on what loading it may experience in transport. So this is the kind of recommendation that we have in the guideline, that we're looking at different road conditions. You can see, You can see our different road conditions where we're going over a more bumpy road, and that might impose different loadings on the structure itself. So that kind of consideration is what we're recommending in the guidelines. And also we conducted some physical testing. So connections in modular design are incredibly important because at the end of the day, all these modules are being connected together. So to verify some of our connection recommendations. We've done physical testing here. Here's some various steel connections. And then we're comparing those to finite element analysis and showing that we have the same failure patterns, the same failure locations, and using that information to better inform the guidelines. Another provision for modular construction which needs to be looked at is progressive collapse. So if a whole module fails for whatever reason that may be, does the rest of the building then remain structurally sound, or is it of risk of falling over? So what we actually look at here is then the recommendation that if a module is removed, we've got the one on the right, which is falling over. And that's the type of analysis that you'd need to then look at in actually designing for a modular structure. But it may not be without actually being in the guidelines, something that's typically thought of. But by changing those member sizes, it's actually an important process to make sure that a building is appropriate for that situation. So we'll look at a few case studies that our group, or a few projects that our group has been involved in, how we take that modular way of thinking into our designs, and also a few of the other ways of thinking that we take from the different perspectives in our group. So we aren't just engineers, we have physicists working for us, architects, a couple of guys in our lab who are able to do the physical testing, and it's all those different perspectives which we like to bring into a design to give a solution which people would call innovative, but we just call it a different way of thinking, effectively. So the first example is this spec connection system, which we've been prototyping and designing for modular construction. So effectively, it's a very simple connection between two steel columns. So we prefabricate up an entire frame, and then there's a single bolt which connects the two columns together. So very quick to install, very simple installation as well. I've got a bit of a video which will show you this. Basically, a frame gets dropped into place by a tower crane. The guy goes along on the scissor lift, and from above, he's able to access the bolted connection. Threaded rod feeds down to a box bolt at the bottom. Basically, that clamps the two columns together. So there's no temporary propping required. It's a very simple, very quick installation process. So we're saving on time, we're saving on materials, and also on the labour on site. So basically, just as an example, how thinking differently about quite a standard thing, a steel-to-steel connection, can result in significant improvements in the design. And that's, again, just accessing from the top, a very simple installation. We'll give a bit of a physics lesson for this one. James's concept for the elliptical energy pathway theorem, which we call EEPT. So basically, this has got to do with how energy flows through a building, how we can better harness that and better direct it in ways that are more efficient. So if we think of a building as a mass basically on the end of a pendulum, so this is able to move freely. This is a very simple model of a building, and we'll slowly develop this a bit more into a bit more detail. If you think of a pendulum, it's a bit like when you're walking, your body is constantly moving over the top of a pivot point, and by doing so, it's keeping in balance. But if you stop or don't put your next foot out, you're going to be off balance. So a classic mechanics problem is, how do you stabilize this pendulum if you've got a movable cart underneath? And what do you need to do that? What frequency are you moving that at to actually stabilize the system? This is a little bit like if you're trying to balance a broom out on your finger. You might have done this as a kid, or maybe a bit more recently. It's a bit difficult to do, and you're constantly moving to readjust. So it's a very unstable system. So if we try and make this a little bit more like an actual building, we then add a spring to the base of our model. This could be representing the connection between the columns and the foundations, and basically provides that stiffness that prevents a building from basically falling over. And if we take this and then look at it mathematically, we've got some pretty simple equations as to how this is going to act, what the frequency of the motion is going to be. And we can then predict how it's going to move. It's a little bit like a metronome in that you get a certain frequency out of it. You can increase the stiffness of the system, change how that's going to act, what the frequency will be. And effectively, this is how buildings are thought of. You increase your stiffness or add, say, a tuned mass damper or other measures to a building to try and control how it moves. We look at how it moves, basically just back and forward as one rigid system. So a very simple way of thinking of a building, very simple way of designing, but it is often the way that it's done. But if we look to nature and the structures that occur in nature, this isn't how they're actually designed or evolved. They move much more freely, much more naturally, and allow the energy to transfer throughout an entire structure. So here we've got our blades of grass, which are able to move. You could think of like a bamboo structure, which is quite stiff in its individual pieces, but because it has a lot of flexible joints, can still move freely and doesn't break under wind loading. So what happens if we then take these concepts and start to apply it to an actual building? How can we take this way of thinking into designing for a structure in the first instance? Well, now our model for the building is going to include a second joint, again, making it a little bit more complicated, but this allows another degree of freedom, another way that the structure can move and transfer that energy. And our equations become a little bit more complicated. I'm a bit past me as well, but we can then start to use those equations and actually model more accurately how a building is going to react. And if you're thinking of how these equations are actually acting in the first instance when you're designing, you've got a better understanding of how, say, the programs which are using these exact equations are acting as well. So you're designing to how they are actually analysing the building. Basically taking that base understanding, which we like to think, by having that basic physics, the basic mathematics and science, we can take our engineering a step backwards and actually go right to the heart of a problem. So now if we compare that to our original example, we've opened up, like I said, that additional degree of freedom in how the building is moving, or how a simple model for the building is moving here. And it's a much more natural way of transferring the energy throughout the structure. And we can take it a step further and say in this example, we would have a flexible joint on each floor of a building. So now our column to floor connection is more flexible. And we allow the structure to move. This is kind of counterintuitive to you want to stop a building from moving, but here we're allowing it to be more freely moving in a load. And in doing so, we can actually transfer that energy throughout the structure a lot more efficiently. And when we look at I don't know how to make that video play actually. Oh, there we go. Cool. So when we actually model this up, and like I said, we've got our guys back in the lab who are able to create our physical models. And we can see we make this model flexible so that when we have a different frequency of loading there, it's reacting in different ways, and we can quite clearly see how it's doing so. So we think that's also a really important aspect to the design in that we physically demonstrate, and you can see that equation I had up before doesn't mean anything to most people in here. But once you actually see that in action and how designing a building to that results in a different way that it's acting. And that's really the lesson I'm hoping to get across from this one, that by taking into consideration those basic, the physics and the maths behind it, that we actually end up with a more efficient or a structure that acts differently and maybe doesn't require the additional measures to prevent all that movement in it. Another great example, which I'll run through, is the New Perth Stadium, which our team was quite heavily involved in. So quite a large-scale project. And we were brought in with a fairly broad scope as to what we might be involved in. So along with some general value engineering, we looked at the roof structure, basically taking out all the steel from the structure by changing member sizes and consolidating. The main area that we looked at was the connection between the roof truss and the rest of the structure. So again, this came from a concept that James had been thinking of, and we took it further and developed it. And it's basically to simplify that connection so it's quite simple to construct, and a lot of it could actually be done off-site or before erection. So this is the connection design. For a fairly complicated situation where we've got 3 members coming in all at different angles, wanting to connect to that 1 member below, we've now got them rotating around a single pin, which is our cylinder. I'll go into the breakdown of the components of it. There's another view from above. And basically, it's a lot simpler than having 3 individual members all individually pinned. The installation of this, or the installation is a lot simpler. Basically, that's our component breakdown. We've got our 3 members, which, although they now have a ring section on the base, which allows them to rotate around our hinge, that can be all prefabricated off-site. So it does bring some complexity to the design, but nothing that isn't able to be done in a controlled environment. And then for the actual installation, it's quite a simple process. We're basically threading those members with a single hinge. And I mean, to me, it seems like a pretty obvious solution, but I haven't seen anywhere else where a design like that's actually used. So, as is often the case with things like this. So it's a little bit different to how it was actually installed. What we ended up doing was installing the connection on the ground. So we're, again, taking that complexity out of a more dangerous situation from working at heights. But effectively, we start off with our fork plate, which has a position for each member to be inserted into. Our members each go in to their own position, and again you can see that ring connection at the base of the members. That gets threaded by our cylinder and capped off on either end by a plate. So a pretty simple way of connecting those 3 somewhat complicated members. And we did some in-house structural analysis, so finite element analysis on the connection. And what we can see here is, because we're now spreading that load, it's more of a distributed load rather than a pin connection which creates a point load. We don't have any stress concentrations under even quite severe loading that you'd expect for this significant roof structure. We're able to, as I say, spread the load and create a much more efficient connection. So an important aspect for this, like I was saying, is that a lot of it can be prefabricated off-site. So here we've got the fork plate and the connections being tested in there for fit, and a lot of this work is able to be completed by the steel fabricator, which we had a lot of input in from as to how we could make it more, I guess, easier for them to construct, both in terms of fabrication and when it does actually get installed on site. So again, we think that's quite an important aspect about our designs, taking input from another perspective, from the guys who are actually going to be building this in the final instance. And it's not something that you'd potentially think of as actually being modular, but the roof trusses themselves were all prefabricated up in these huge elements, which are effectively just a big modular section. They're then transported to site on customised rigs, which basically get along on the back of a truck. So all designed in with that fabrication and with the delivery in mind. And then, like I was saying, on site, we've actually installed those 3 members which hold up the roof truss while we're on the ground. So we basically just lift that up, and it's quite a simple installation from there. We're bolting a plate to the column. And one of the big benefits about this connection was that we can actually have that flexibility in finally positioning the roof truss. So that rear member which we see going on there can be adjusted in terms of its height, and that adjusts the overall RL, or the overall position of the roof truss. And that's what we gain by actually having that flexible or hinge connection there too. So just to sum up, we really do hope that the modular construction code, that it is adopted in a way that promotes better or smarter modular design, and brings a bit of clarity into how modular should really be designed for. Our group's really big on the sustainability of our designs, on reducing our impact both on site and overall in our material usages. And we see modular design as a real way of progressing from conventional construction methods. I know coming from an engineering background, having dealt with some of the Australian standards, they can be a little bit difficult to interpret at times. So we've really tried to make this more accessible and applicable to real-life scenarios where will hopefully be more widely adopted as well. So thank you very much for your time. Like I said, we do have the code already in your packs. And if you would like to hear a bit more about the modular construction code, we do have other presentations taking place in our room in, I believe it's Stream E. So be happy to discuss further then as well. So thank you very much.